This work has been done in my previous university at Virginia Tech. Currently, I am at New Mexico Tech. And this work was a collaboration with several scientists like Sarah Stamps, John Naliboff, Andrew Nyblade, and Emmanuel Njinju from Virginia Tech. So today, I'm glad about the previous talk because today I'm gonna really talk about more details and the numerical modeling perspective of how the mantle flow beneath East Africa interact with the lithosphere and drive surface deformation. And the main goal of this talk is to understand what is the driving force of the East African rift. So to start, I would like to define what are the forces that could potentially drive continental rifting. The first force is lithospheric buoyancy forces, which is due to variations in gravitational potential energy, which is due to topography and density gradients. And you can see an example, a good example at the mid-oceanic ridge, where you have large topographic gradients. So you have a force driving the formation from high to low topography. The second force is called mantle traction, which is due to the interaction of the mantle flow with the base of the lithosphere. And the mantle flow could be due to the plume or large-scale mantle convection or even small-scale convection. The last force is slab pull forces, which is due to the gravitational collapse of the subducting plate, as you can see in this figure. And today, I'm gonna focus mainly on the first two forces because the East African rift is remote from slab pull forces. And it is highly debated which one of the lithospheric buoyancy forces or mantle traction is driving the rift. So the East African rift is comprised of four main tectonic plates: the Nubian plate, the Victoria block, and the Rovuma block, and the Somalian plate. And as you can see from this figure, the East African rift has a really unusual high topography, as you can see from this yellowish color. And the East African rift is surrounded by oceanic region, which generate a perfect setting of high topographic gradients. And the rift is opening the Nubia-Somalian plate system in an east-west direction, but the origin and the driving force of this, the nature and the driving force of this opening is highly debated. But what is interesting with the East African rift is that there are anomalous surface deformation, anomalous geophysical evidence that is inconsistent with this east-west extension. One of the good examples are the GPS velocities that you can see in blue vectors. And you can see that some of these velocities are rift parallel motion, northward component of motion. The second anomalous geophysical observations are the strike slip focal mechanism. So they are evidence of strain partitioning by rift parallel motion. And the last but not least is the seismic anisotropy. They are rift parallel, and in a normal rift setting, you would expect that the seismic anisotropy would be perpendicular to the rift. And in 2013, Bagley and Nyblade have suggested that this northward rift parallel seismic anisotropy is due to a large scale mantle flow rising, moving upward from beneath South Africa and moving horizontally northward to beneath the East African Rift and up to the Afar region. But this northward mantle flow known as the African super plume is not the only mantle flow model in the East African Rift. There are some authors that suggest that there are distinct plumes beneath distinct rift segments, like as in this figure. So our main goal is to test the hypothesis that the northward component of surface motion is driven by viscous coupling to the northward mantle flow associated with the African super plume, but we tested also if it is due to the multiple plumes. And we suggest that this northward mantle flow associated with the African super plume is the main source of the seismic anisotropy. So to do this, we have used a very sophisticated numerical modeling. And in this talk, we try to, in this research, we try to calculate the surface deformation and compare them with observations. So in this talk, the dynamic velocity that I'm going to compare with the observations are the solution of the Stokes flow equations, and we use the open source code aspect for that. So it's solved for the conservation of momentum and the conservation of mass. The conservation of momentum is the force balance between buoyancy forces, which is balanced by viscous resistant forces and the pressure gradient forces. And the divergence of the velocity is 0. So there are different assumptions in this type of modeling, but one particular that I'm going to talk about is the rheology. So we use a nonlinear rheology that we assume diffusion and dislocation creep. And in this formulation, the viscosity depends on temperature and the strain rate. And in the sublithospheric mantle, we use diffusion, a composite rheology, which is an harmonic average of diffusion and dislocation creep viscosity. And in the lithosphere, we try to mimic the real Earth. So we have the yield strength of the lithosphere, which is a function of pressure, the cohesion, the angle of internal friction, and the cohesion coefficient. So I want to emphasize that the lithosphere is very strong even within the rift. So we have to apply plastic strain weakening by reducing these two coefficients, the angle of internal friction and the cohesion, so that the yield strength of the lithosphere is reduced to localized surface deformation. So in 2D view, I'm showing here the geothermal strength of the lithosphere from different domains, the craton domain, the mobile belt, and the rift domain. And you can see craton has a very thick lithosphere, so very cold geothermal gradient, and it corresponds to a very strong lithosphere. And the rift domain here has the hottest geothermal gradient and generate strong, the weakest lithosphere. But here, if you look at this value in the upper crust in the rift, the largest strength is up to 150 megapascal. So there is no force on Earth that even able to break this lithosphere, because the available forces in the East African Rift is very much lower, up between 10 to 20 megapascal. So it justifies our use of plastic strain weakening to localize deformation. So this is a 3D view of our model. And you can see we have taken into account the cratons that you can see in cold color, very strong lithosphere. And with a warm color the regions across the reef that we have applied plastic strain weakening. So one particular, so the difference between this model with a typical continental reef model is that we don't apply the outward velocities that is driving the rift, but we use surface topography to account for variations in gravitational potential energy so that the rift is driving by itself.
Here you are 10 minutes now.
Okay, so the three models that I'm going to compare in the next slides are the model one. The model is only driven by gravitational potential energy, the lithospheric buoyancy forces, and you can see here the variations in gravitational potential energy from in the mainland high GPE and low GPE in the oceanic region. In the model two, we have converted shear wave tomography from Embry et al. 2019 into temperature anomaly, and it generates density anomaly and generate mantle flow. So we have added beneath the lithosphere a mantle flow, and you can see here the pattern of the mantle flow from the multiple plume model. We have outward mantle flow that are perpendicular to the rift. And the third model is a super plume model where we have this, we simulate with a northward boundary condition to simulate the northward mantle flow from the super plume. And the mantle flow looks like this, that is mainly characterized by mantle flow going around Tanzania Craton and flow parallel to the rifts and flowing northward. So here, I compare the surface velocities, the kinematic models with our dynamic velocities. Dynamic velocities are in red and the kinematic velocities are in blue. And you can see from the lithospheric buoyancy force as a driving force only can already match the surface, the kinematic model. We can observe the clockwise rotation of the Somalian plate, the counterclockwise rotation of the Victoria block, and the clockwise rotation of the Rovuma block. All motions are with respect to the Nubian plate. But you can see that whenever we have, when we have a mantle flow beneath the lithosphere, we can see that the surface, the dynamic velocity are larger in terms of magnitude, and the velocities of the Somalian plate is up to 2 to 3 times the rotation rate. We can see that also with the super plume model. But so in this case, we suggest that our use of the viscosity may be different. The viscosity beneath the East African rift may be anisotropic, because we know that there is mantle flow, but the lithospheric buoyancy force can already explain the rotation rate. So maybe the viscosity may be very strong to the east and weak to the north, so that we can match this surface velocity. We have also compared the surface velocities for, in the deforming zone. And you can see with the lithospheric buoyancy force only, we have very much worse fit in terms of angular misfit in some segment of the deforming zone, like here in the western branch, here in the Ethiopian rift, and here also in the central segment of the western branch, where we have like really mismatch between the observations and our model. But whenever we add the super plume, we see that there is improved fit between the angular misfit within the rift segments. So we conclude that the metal traction from the superplume can drive and influence surface deformation in some region of the East African rift. We have also calculated seismic anisotropy, and we could see that the multiple plume does not really explain the anisotropy, as you can see for this from this worse misfit in different regions. But the superplume model, we have very good match between the calculated seismic anisotropy and the observations. So we can say that the superplume model can explain the seismic anisotropy and the northward component of motion. So to conclude, we can say that the rotation of the blocks and the plate kinematics can be explained by lithospheric buoyancy forces only in the East African rift, and the viscous coupling associated with the northward mantle flow associated with the African superplume influences surface deformation. And we found that the multiple plume does not really explain the superplume does not really explain the rotation rate of the Somalian plate, but we can argue that anisotropic viscosity could explain the presence of the mantle flow beneath the East African rift. Thank you very much.
Thank you, Tahiry. There's time for one quick question. If you have it, just raise your hand. Someone raised a hand. Amiha.
So thank you so much for the very interesting talk. And I have one quick question. You showed that there is a north or rift parallel motion constrained by GPS velocity vectors. Mm-hmm. And you argued that this is due to viscous coupling between the asthenosphere and the overlying lithosphere. But this area is very hot, and so there is a high geothermal gradient, and usually the viscosity should be high, and this leads to decouplings. So what's your comment on that? Because I expect there is the decoupling between the lithosphere and the asthenosphere. So, and here you said it's a coupling. So what's your comment on that? Thank you.
Yeah, very good question. Previous studies have suggested that there is viscous coupling between the craton. So there is like the coupling is favored by the strong lithosphere, and the coupling between the mantle flow and the lithosphere. But as you said, there is a contrast. Beneath the lithosphere is very strong, and there is a very strong contrast between the lithosphere and the mantle underneath. But if you look at the rift, the viscosity is weak beneath the rift in the mantle lithosphere. So there is no much contrast. And if the mantle is flowing faster, very fast, there could potentially coupling, and our model is kind of capturing some of this coupling. So you have to quantify that, like how hot is it, and like what the viscosity looks like, in order to really justify that there is no coupling because of the high temperature.
Okay, thank you.